Alrighty, so begins lecture 6 on the so-called Frenet Serret frames for curves in R3. Some multivariate calculus or third semester American calculus courses would cover this, but I think it gets lost in the shuffle sometimes, so that's unfortunate. Basically, our goal here is to describe a certain frame field that we can attach to a curve. Alright, so I'm going to just go ahead and show you, roughly speaking, what it looks like. So here's a curve, whatever, and we're going to assume our curve's alpha, some interval, open, closed, whatever, of real numbers to R3, and usually we'll assume that it is a regular, maybe we always assume that, regular curve. So that means that alpha prime, and we're going to assume that it's arclength parametrized, alright? So alpha prime of S is not equal to 0 for all S in I. To say it's arclength parametrized, I can't spell. Arclength parametrized is to say that the length of the velocity vector is 1. Of course, the length of the velocity vector is also more generally ds dt, but in this case it's kind of ds ds, right? So, alright, so arclength parametrized regular curve. And often we're going to assume it is nonlinear. But I don't want to assume that at the outset. Alright, so I will be ignoring Isaac for the moment. Go away, Isaac. Daddy's working. See you, buddy. Okay, so at a point, we have the vector which points in the direction of the curve, which we'll call the tangent, or unit tangent, to be more descriptive. We have then a normal, the Frenet normal, which points something like this. Yeah, I use an n for that. And then the binormal will form by b will be equal to t cross n. Of course, that will be perpendicular to both t and n because it's a cross product, right? So it'd be something like that, or perhaps still not quite the right length, but something like that. All right. And then you can imagine, right, let's see here, you can imagine as you go along the curve, let's see here, something like this, So you go along the curve, right, and as you go along the curve, the tangent has to point in the direction of the curve, and then actually, this would actually, if it did that, I would have to, how to do this? Like, it'd have to flip over. It would have to flip over as it went from here to here, because the Frenet normal points towards the center of, if you were to fit a circle to the curve, the Frenet normal always points towards the center of that circle. That circle is called the osculating circle to the curve. So it'd be like that, so like that. Alright, but we want to describe how you can attach this Frenet frame at each point along some curve in a systematic way, and then we're going to derive this Frenet Serret equations. Alright, so let's get to it. Definition T is equal to, let's see here, alpha prime. Alright, that's it, because, and that's it, that gives me, by the way, t dot t, right? There's a definition. T dot t is alpha prime dot alpha prime, but that's the norm of alpha prime squared, which by the way is 1 because we're assuming it's arclength parametrized. Alright, so there's the tangent. The normal, actually, we'll get from observing something. So if I have t dot t equals to 1, right, then I can differentiate that, right? And if I differentiate that, that gives me t prime dot t plus t dot t prime equals to 0. Okay, great. And then that tells me, since that product commutes, that tells me that, well, 2 t dot t prime is equal to 0. So, aha, we can use t prime to obtain a perpendicular direction to t, to the tangent, right? And so if you normalize t prime, then that gives you the normal vector. Okay, so the normal vector n would be equal to t prime normalized, so I divide by the length of t prime. All of this with respect to the arc length parameterization, and that gives you, of course, a unit vector by construction, right? So there you go, there's the definition of the normal. And in tune with this, we also define the curvature to be the length of t prime. Again, to be more specific, t prime is actually ttds, all right? And you might worry that these things geometrically are going to depend on my choice of parameterization, right? I mean, I've chosen the particular parameterization. Well, that's the thing is, it's not a particular, it's a very specific parameterization. It's the arc length parameterization. So up to a choice of a base point, right, saying arc length is 0 at this particular point, this actually is unique, right? There's just one arc length parameterization modulo a shift for a curve, and that's why these definitions are actually geometric, despite the fact that I'm using a parameter to define them, all right? So there you go, there's your normal, there's your tangent. And then you need a third direction, so I already gave you the definition up here. There's the binormal, all right? Okay, so tangent, normal, binormal together, these give you the so-called Frenet frame to the curve, right? So I will, oh, I forget, what did I do? I guess I drew a circle dot B out of the page. So what we'd like to do then is to understand how these vector fields along this curve alpha, right? How these vector fields evolve with the curve, right? And so we already have one of those things here. I mean, if you look at even what we have by definition, this gives us that t prime, right, is equal to the length of t prime times n. So if you rewrote that in terms of curvature, that's kappa n, right? And so that right there is one of the so-called Frenet Serret equations. All right. But let's be more systematic. Let me show you. Let me state them all and prove them. It won't take us too long. All right. Page number 2, lecture 6, I believe. All right, where am I? All right. So here we go. We define normal, tangent, binormal, just as we did, and given those definitions, we get the so-called, given T, N, and B for alpha arc length parametrized. As we just defined, there exists another function, tau, all right, which we call the torsion, for which, all right, and we're going to discover what has to be the definition of the torsion as we derive this theorem here, okay? So dt ds, but I'm getting tired of writing, I'm going to write that at t prime. Okay, t prime equals kappa n, and I'm going to write them as and n prime equals to minus kappa t plus tau b, and b prime is equal to minus tau n. All right, where again tn and b are the tangent, normal, and binormal. All right, so most of this proof rests upon the observation that Tn and B together form a frame. So let's just settle that to start with. So T is, of course, alpha prime, right? And I guess more generally, I mean, I don't need that, but it's if we had a time parameterization rather than arc length parameterization, we have to divide by the speed, but we don't here, so it's just alpha prime. Okay, great. And of course, T dot T is equal to alpha prime dot alpha prime, which is equal to 1 by assumption. But that says that T prime dot T plus T dot T prime equal to 0. Therefore, T dot T prime divided by the length of T prime, right, is equal to 0, provided what? The curvature function, which is the length of T prime, is not equal to 0. So I guess I have forgotten something which is kind of important. Alpha arc length parametrized curve, non-linear, right? So non-linear means the curvature is not equal to 0, all right? In fact, if you go back to the previous lecture, the curvature being 0 would be given to us for arc length parameterization if we had alpha prime prime equal to 0, right? Alpha prime prime equal to 0 would mean that T prime was 0, which would mean that the magnitude of T prime was 0, which would then give curvature 0. So curvature 0 corresponds to a line by a proposition in the previous lecture. Okay, so suppose we have nonlinear case, then we can normalize like so, but of course this is n, right? And so therefore T dot n equals to 0. So we have orthogonality of the tangent and the normal vector, and as the binormal is defined to be the cross product of T and n, it follows, right, that T and B forms a frame, right? And since they're a frame, that means they're orthonormal. Since they're orthonormal, it means it gives us a basis for the tangent vectors based at each point along the curve, all right? So with that in mind, as we think about this, right, we've got this curve, right? We take a particular point, which would be alpha of t, right? And then we can analyze these three vectors, t prime, n prime, b prime. Those are also vectors along the curve because they're formed by differentiating t, n, and b along the curve, as we carefully defined in the last lecture. Now, we already know that the first equation here is true. That's essentially the definition of the curvature. It remains to show that this equation and that equation are true, all right? I'm going to start by focusing on b prime. So consider b prime. Well, that has to be equal to what? Well, that has to be equal to b prime dot t plus b prime dot n plus b prime dot b, because t and b is a frame. So that's the components of b prime with respect to said frame. Since b dot b is equal to 1 by construction, that tells me that b prime dot b, actually twice it, fine, by the product rule is equal to 0. So therefore b prime dot b is equal to 0. Okay, so that term is toast. There, it's gone. Adios, muchacho. Then we also, what else do we know here? We know that, let's see here, do I have b somewhere in here? Oh, of course we also know that n dot, excuse me. We also know that b dot n is equal to 0, right? Let's check that out. So my marker will come undone. Fine, it's a different color. The marker's not cooperating. Observe b equals to t cross n. Well, that tells me that b is perpendicular to t and n. So, I mean, I get two different things from that. The one thing I get is that b dot t equals to 0. I also get that b dot n is equal to 0. All right. So for some reason, I believe that there should be an n left over. That makes me want to pick on this term. So I'm going to investigate b dot t equal to 0. Differentiate this. What do we get? We get b prime dot t plus b dot t prime equals to 0. All right, great. Now, what is this? Well, b dot t, so that gives us b prime dot t is equal to minus b dot t prime. But what is t prime? T prime is minus b dot, well, t prime is, it's kappa n. But kappa is just a scalar function. You can pull that out to the front. And so you got minus kappa b dot n. Hey, that's 0. All right. So there you go. B prime dot t is also 0. Now, you might worry that this forces you to get 0 for b prime dot n, but in fact it does not. The reason for that is, well, it's actually kind of complicated from the moment. We need to know what n prime is to answer that, so let's just not scratch that itch just yet. So all we're left with is this, all right, for b prime. So basically we just say, okay, so let the torsion tau equal to minus b prime dot n, then we have that b prime is equal to minus tau n. You say, why the minus? Well, convention, all right, if nothing else. It's just a choice in labeling, but there it is. So b prime is minus tau n, and we have justified the existence of this function in just this function because the other two coefficients are necessarily 0 because of the other properties of the frame. All right, so now that we have that, we can come back and attack n prime. N prime then, all right, n prime, oops. N prime is also going to be equal to, again, using the frame, n prime dot t, t plus n prime dot n. We know this term is going to be 0 because n prime dot n, n dot n is 1, which is going to give me n prime dot n is equal to 0. So let me just go ahead and nix that. That's going to be 0 by the same argument we just given a couple times. Now, n prime dot t is going to be equal to minus n dot t prime because we know that n dot t is equal to 0, right? So n dot t equal to 0, differentiate gives me that n prime dot t plus n dot t prime equals to 0. And because you have that little identity right there, I can do that, right? But if I have minus n dot t prime, well, t prime, we already know what that is. That's minus n dot kappa n, right? Which is just minus kappa, right? And then, likewise, we can do the same kind of argument for n prime dot b. N prime dot b is equal to minus n dot b prime because n dot b is equal to 0, right? And you differentiate that to get this exchange of derivative for minus, right? And then that's minus n dot, well, minus tau n by definition of torsion. But n dot n is 1, so that gives us just torsion. Lo and behold, we see that this term goes to minus the curvature, and this term goes to the torsion. In other words, this is minus kappa t plus tau b. And that, well, that's exactly the Frenet Serret equations. So there you go, that's how it goes. Simple as that. You might not think it's simple. I think you do, if you're watching this. It's really just, again, this beautiful use of the orthonormality of the frame, plus the product rule differentiation. It's just that. It's not so bad. 3. Now, I can imagine an unsuspecting Calculus 3 student trying to prove these things using components. That would be bad. That would actually be rather hideous. Okay, so anyway, you see that we now need to make a definition, just to be clear for future purposes definition. The torsion is equal to minus dB ds dot the normal. And that's for alpha unit speed, which is another way of saying arc length parametrized. Unit speed, nonlinear, regular. Probably I should put those in the opposite order. Regular curve, all right. Torsion. All right. Now, so we should probably do an example. I should probably, well, fine. Example. I guess you can always fast forward if you're bored. Alpha of s equal to, excuse me, r cosine ks, r sine ks, mks. And here k is equal to 1 over the square root of r squared plus m squared. To keep it interesting, I guess we're supposing at least r or m is non-zero. Otherwise, it'd be kind of a pain. All right. So this is called a helix, all right? And I have constructed it to be unit speed. You can calculate the velocity, right? Would be, let's see here, minus r k sine ks u1 plus r k cosine ks u2 plus mk u3. So if you calculate the length of alpha prime, we get square root. You get a k, so you got k squared. This gives me r squared sine squared, r squared cosine squared, so I just get r squared. And then plus m squared. But as you can see, k squared, right? You see this, these cancel, so it just gives you 1 by construction. That's not an accident. I made that. I chose this k precisely for this purpose. Okay, so, but hey, check it out. There's t. All right. And if you want me to be, I tried to just write t, not write t of s, because writing the of s, okay, fine, to be more careful, t of s, whatever. All right, so t prime then is what? Well, all right, so use a different color. T prime is, well, let's see here, differentiate brings out another k, so I get minus r k squared cosine ks u1 minus r k squared sine ks u2. This piece goes to 0 because it's a constant. And okay, so you can see then that the length of t prime is r squared k to the 4th, right? R squared k to the 4th cosine squared plus sine squared, right? Same term. So that goes away. So we just get square root of r squared k to the 4th. So it's just r k squared, right? But you should recognize that as being r over r squared plus m squared. Check it out. There you go. That's the curvature. The curvature for this helix. So that's the curvature of a helix. Curvature. Circular helix, of course. There are other kinds of heli. I don't know what's a plural of helix anyway. I don't know. Helixes, whatever. All right, so there you go. And this gives us n as cosine ks u1 minus sine ks u2. So there's my normal. My tangent was up there, right? Okay. Now the binormal in our current way of thinking, I've got no choice but to calculate a cross product. All right, so t cross n. And when you work that out, what you get is mk sine ks u1 minus mk cosine ks u2 plus kr u3. And that's just taking the cross product of t in an unusual way. So there's the binormal. Now, you can check that the length of this is 1 because we get m squared k squared sine squared cosine squared. Let's go away to give you 1. So you get m squared k squared plus k squared r squared. But that's r squared plus m squared over r squared plus m squared when you work it out, which is 1. Okay, it has length 1. You can check. Good check. All right, so b prime is, what is it? It's mk squared sine ks u1 plus mk squared sine ks u2. Oh, no k dependence, so that's 0, right? So there's a derivative of the binormal, and you can check, right? b prime dot n is what? Well, here's n, here's b prime. Take the dot product, we get, oh no, I can't differentiate. You know, funny thing, when you differentiate sine, you get cosine. Okay, that's better. So cosine squared, and this is sine squared, actually you get a minus cosine squared minus sine squared mk squared. So we get minus mk squared. All right, well, that's equal to minus the torsion. So therefore the torsion is m divided by r squared plus m squared. There you go. That's the torsion of a circular helix. Now, if you really want to think about it, this is a lot of fun because it really has pretty much the whole geometry of the Frenet frame. I mean, this example is not that hard, right? But it actually has a lot in it because it kind of tells you what's going on. So to start with, you've got, you know, yeah, I should put it up here. The normal, I mean, here's the tangent, right? Tangent would be kind of like pointing into the page, like that, something like that, right? And then the normal, it points towards the center of the, you know, circle around which you could just put the circle. I mean, if you fit a circle locally to the curve, then there'd be the normal. And then t cross n give you the binormal, which is pointing upward here, right? And so what happens as you go over to here, the let's see here, the normal, well, let me go just a little bit closer. So it's like right here, and then the normal, it always points like that. It's hard to draw in perspective, but notice the normal has no z component. It's horizontal. So it's like if the helix is going up, it's like the normal just kind of traces. You probably can't tell in the, oh well. Anyway, the point is the binormal then t cross n, you know, something more like that. And so as you go along the curve, the binormal, it changes, obviously, right? And this says that it's, if m is positive, as it is I've drawn for this curve here, the torsion's positive, that means that b prime dot n, it's the direction of the change of b is what? It's minus, it's in the normal direction, so b is like, it's like evolving into the normal direction. And what else? It's negative, so it's well, I don't know if you, I sometimes am successful in seeing it. Anyway, there it is. Oh, okay, another interesting limiting case, of course, if you take m equal to 0, the helix collapses to what? Just a circle. And so you can see that the torsion is equal to 0 for a circle, and the curvature is equal to r over r squared, which is 1 over r. So that provides an interesting and useful bit of information for us. A circle apparently has curvature which is constant and reciprocal to the radius, and a circle has zero torsion because, well, basically if you go around a circle, right, like this one, well, anyway, here's actually, this is actually any old curve, right? Think about going around any curve. If the green Lego's the normal and the blue is the, the green's the tangent and the blue's the normal. You see the binormal, it's always just pointing the same direction. It's just distantly parallel. Any of these binormals distantly parallel if my Legos were level. So B prime is not changing, B prime is 0, which goes to show you, of course, that the torsion is 0 for a planar curve. This is a specific example of that. Let me move on here. So for actually, that's our next theorem. Let alpha be unit speed, nonlinear curve, right? I guess unit speed already says regular because unit speed says the speed is 1, which means that certainly 1 is not equal to 0, so it's regular. Fine. Unit speed, nonlinear curve, then alpha is planar curve, if and only if the torsion for that curve is 0. Have I gotten off frame? I have. No! Alright, I'll fix it. Sorry about that. I should draw myself some little dots here or something. But then it's going to make a mess of everything. Oh well. Okay, so the proof, let's see here. Let's go with the forward direction. So I'm going to draw a picture, but the proof doesn't really use the picture. I mean, the picture is a guide to tell us how to do the proof, but that's about it. Okay, so here's the curve. If it lies in some plane, right? Let's suppose that the normal to the plane is a constant vector, v, all right? Then if I took two different points, say alpha of s naught, and I had alpha of s, right? These are two different different points on the curve. Then if you look at the vector which connects them, right? And here, okay, so admittedly I'm abusing our setup from before. I mean, so let this be gamma of s. I argue it makes sense to write gamma of s dot v equals to 0. You'd be like, but gamma of s is not a vector. You can't take the dot product with a vector. We'll find them defining a vector in terms of the displacement. You know, thinking of it as that directed line segment. All right, fine. Anyway. Admittedly, it's an abusive notation. All right, now differentiate this. What do we get? Well, again, gamma of s is alpha of s minus alpha of s naught. Okay, s naught being a fixed parameter on the curve. Point. Alpha of s naught's a point. S naught's the fixed parameter. So if I differentiate this, right, what do I get? Let's see here. I get differentiate. Well, gamma prime is just alpha prime, right? So differentiating this gives me that alpha prime dot v is equal to 0 because v is a constant. So I mean I could do the product rule, but v prime is 0. All right, differentiating, which tells me that t dot v is equal to 0, right? And then if we differentiate again, and it gives you t prime dot v is equal to 0 because v is a constant, so I don't really need product rule here. Which tells me what? Well, that tells me that kappa, curvature, t dot v, well, excuse me, not t, n, right? We just got done deriving these things. Oh, curses. All right, fine. Kappa n dot v is equal to 0, but we assumed that the curve was nonlinear, so the curvature is not 0. So therefore, n dot v is equal to 0. So we've got this vector v. It's constant. It's perpendicular to v. I mean, it's perpendicular to the tangent. It's perpendicular to the normal. By the geometry of frames in 3 dimensions, there's only one thing left. That implies that v has to be collinear with b, right? So, and then what? So that means that there has to be b is equal to kv for some function k, let's say, and then what? I say thus b prime is equal to 0. How do I know k is not a function? Oh no. Seems like there's a gap in my argument. Whatever will we do? Let's differentiate. So b prime. Oh, I'm an idiot. Here's a. I don't know that k is not a function though. Huh. Well, maybe I need another Frenet Serret equation here. So then b prime, right, is equal to, what is it equal to? It's equal to k prime v. I feel like I'm missing something obvious here. Plus kv prime in principle, but v prime is by assumption 0, right? And k prime v, well, k prime v is equal to what? It's equal to k prime over k, kv, right? Which is equal to k prime over k b. But b prime dot b is equal to 0, we know that. So that implies that k prime over, well, how can I say this? If b prime dot b is equal to 0, it must be that k prime over k is equal to 0, because if you have b prime dot b, that's equal to k prime over k b dot b, right? But that's k prime over k times 1. That has to be 0, right? So, and we're assuming, of course, k is non-zero. So therefore, we derive then that k prime has to be equal to 0. So therefore, k is equal to some constant, right? I guess it could be plus. I mean, it depends. The constant depends on how long v is. B is a constant vector, right? So anyway, once that's done, that implies, of course, that the torsion is equal to 0, because if you differentiate b, a constant vector times a constant times a constant vector, b prime is 0. All right, this immediately implies b prime is equal to 0. Hence, the torsion is 0. All right. Well, need to fix my notes. It's like, k. Well, k is a constant. Yeah, that's good logic. Oh man. All right. The other direction. Suppose the torsion is 0. If the torsion is 0, then that implies that b prime is equal to 0 along the curve, right? Which implies that b is just equal to some constant vector, right? Some constant vector. And, well, but, also, or if you like, we could say that b of s is equal to b of s naught for all s in the domain of the curve, which I haven't stated up to this point. All right. So, I mean, intuition is that the binormal is the normal to the plane in which the curve evolves. So what we do is we just define a function, all right? And you know, I got this from O'Neill, and I would hope this is in many books, but then again, I don't know. F of s is equal to, we do is alpha of s. So this is basically that gamma we had in the previous argument. Alpha of s minus alpha of s naught dot b of s naught. We'd like to show that this is identically 0. We'd like to show that's identically 0, because then we'll show that the curve is the difference vector between the displacement between any 2 points on the curve is always perpendicular to the binormal, which then shows that the curve is planar. So typical technique here, f prime of s is what? Well, it's alpha prime dot b of s naught, and that's of s if you're wondering. And then well, I guess that's kind of it, isn't it? So that's t of s if you want, dot b of s naught, but of course that's equal to 0, right? For all s, and also f of s naught is equal to what? Alpha of s naught minus alpha of s naught dot b of s naught. So that's also equal to 0. So we have a function which is constant, and its value is 0 at s naught. Therefore, f of s is equal to 0 for all s in I. And so what we have then is that alpha of s minus alpha of s naught dot b of s naught is equal to 0 for all s, right? But of course, we already know that b of s is equal to b of s naught, so that actually gives me that alpha of s minus alpha of s naught dot b of s is equal to 0 for all s. In other words, here's some curve, whatever, and the binormal is the binormal everywhere on the curve. Fine. So the binormal is always distantly parallel to itself at different points along the curve. All right. Torsion. 0 gives planar curve. Great. All right, I'm tired of writing at the moment, so I'm going to zoom in much to my own peril. The next little bit I want to talk about here is the fact that the curvature and torsion allow us to give a local approximation to the curve in terms of arc length, right? So here it is. This is just Taylor's theorem, right? Oops, let me use the proper pointing. Where am I? Oh, come on. Who stole my lightsaber chopsticks are gone. What? Come on. Children. Oh man. What? Someone stole my lightsabers. Oh well, marker will have to do. So this is Taylor's theorem, right? Now I would expect that the first two terms just involve the tangent vector, right? Because those are like linearization. And that is in fact what we'll derive here. Alpha prime prime is t prime, which is kappa n, right? On the other hand, of course, alpha prime is just t of s naught, right? So you get t for the linear term. You end up picking up a curvature and a normal term for the squared term. The s cubed is where the torsion comes into play. Let's see here. So, yeah, so here's what we figured on the last page. The first to second order, we have unit tangent for first, so this is basically linearization. This is a second order approximation with respect to arc length. You notice the curvature is appearing. So if your curve is actually a line, then this would be gone, and that would just be it. Although I don't know what torsion means for a line, so don't ask me. Now, alpha, the third derivative, right, it's so differentiating the second derivative is kappa times the normal, right? t prime, alpha prime prime is t prime, which is kappa n. So if I differentiate that again, I have the product rule, right? I have the derivative of the torsion, excuse me, derivative of the curvature with respect to s, n plus kappa n prime. But n prime by the Frenet Serret equations is that minus kappa times tangent plus torsion times the binormal. And so it gives you these three lovely terms for the third derivative, and then you put them back down in here, and there you go. Now in O'Neill he only has like up to second order in this, but this you'll find in kernel as well. So there it is. There's the approximation of the curve in terms of arc length and curvatures and torsions, as you can see. You could fit like a line to the curve, right? That's tangent line. You could fit a parabola that would be given by the curvature. And there's more. If you look in kernel, he has a couple of other sort of canonical curves that you could fit to a given curve at a given point in terms of the tangent, normal, and binormal. He gives their German names, which I can't hope to pronounce. One interesting thing, of course, is the oscillating circle. Here's its equation if you use x and y based on the Frenet frame, taking the origin to be the point in question. Basically, if the point on the curve is the origin, then that puts the center of curvature in the normal direction. So, and actually y equals to 1 over kappa naught where the center would be. So, there's the equation of that. Great. Now, sorry I'm being lazy here, but I sense lunch is upon me. Oop! Oh no! Oh no! If you have a constant curvature k not equal to 0, it follows a circle of radius 1 over k. So, of a unit speed, nonlinear curve with constant curvature, kappa naught, torsion 0 for all s, then it follows that alpha of s is on a circle of radius 1 over kappa naught. Now, we know that we need the torsion to be 0. If we don't force torsion to be 0, we could have that Helix example, which also had constant curvature, of course, but non-trivial torsion. And in fact, of course, you can have constant curvature and non-constant torsion. That's also possible, okay? Anyway, my first proof is, I think, intuitive, but I got tired of it. So let's go ahead and use O'Neill's proof, because it's better. All right, so where am I? All right. Proof 1. Oh, let's get past proof 1. Proof 2. Where am I? There it is. So proof 2, I think I can write this out. Let's see here. Page 5. Now is the time I usually forget to zoom back out. So hopefully that won't actually happen here. Let's see here. Whoop. Yeah. Whoop. Right, sorry. So proof of what? Of that kappa equals to kappa naught with torsion equals to 0 implies curve is part of circle. That's what we're trying to prove. And so I like what O'Neill does here. He says let alpha be unit speed nonlinear curve, constant curvature. Consider any point along the curve. The normal should point towards the center of the conjectured circle. So let me just kind of draw a picture of what I'm saying. So here's a curve with constant curvature. I guess you're like, you're begging the point. Fine. Just bear with me here. So this is alpha of t1, right? This is alpha of t2. There should be some like center to the circle, right? And if you were to look at the normal vector, or the normal vector over here, they should always point to that same center point, right? That same center C. So I would say that this is R, say Rn1, here's Rn2. The point is that if I take alpha of t plus r n of t, I should like that to be that fixed center point C, right? So, in other words, oh, and I'm using t, but I really should be using s because I'm assuming that this circle is arc length parametrized. So I try to use, so let's just say t is equal to s, that will fix me. I mean, it's not written in stone that you can't use t for being arc length, it's just, you know, I try to use s for arc length. Alright, fine. So let gamma be this curve right here. Gamma of s, alpha of s plus Rn of s. We'd like to show that that's constant given the data that we have. So here we go. Gamma prime of s is equal to alpha prime of s. Oh, look at this, all this s dependence I'm writing. My goodness. Rn prime of s. Fine. I'm dropping the s dependence here pretty soon. No, not soon enough. Alright, anyway, so t of s, and then n prime is what? Well, well, ordinarily it would have two terms, right? R, and n prime would be what? It would be minus the curvature times what? Times t of s plus the torsion times b of s. Oh, all this s dependence, so hideous. Alright, but of course we're given that the torsion is 0, right? So what we have then is we have that gamma prime of s is equal to t of s minus r kappa t of s. So you see, I forgot to say this, but how should we choose r? Well, it's quite clear how we should choose r now if we want this to be 0. This will be equal to 0 provided we do what? We set r equal to 1 over kappa naught. Remember, kappa of s is equal to kappa naught for all s, alright? So if we do that, hence gamma prime of s is equal to 0 for all s. And what's that give me? So that means that gamma of s naught is equal to gamma of s for all, for all s. And let's see here, what do I say? So I say let c equal to gamma of s naught. So what we have then is alpha of t is equal to c minus Rn of t, right? I'm using t again. Sorry. anyway, so, or if you like, alpha of s is equal to this constant vector c, point really, minus Rn of s. And as you can see, the length of alpha of s minus c is equal to r for all s, which goes to show you alpha's on a circle, centered at c with radius r, which is the reciprocal of the constant curvature. Alright. I mean, you can look at my proof number 1 here. This is proof number 2 in my notes. Proof number 1, I mean, I got so far, but I'm kind of stuck on the differential equations at the end of it. And this proof is so much simpler, so I decided to share this with you here. Alright. So that brings us to our last example, which I'm going to use the projector for as to not be too long-winded here. It's very simple. If you have a curve on a sphere, then it's at least as curved as a great circle on the sphere. So suppose the sphere has center C and your alpha lies on the sphere, that means the distance alpha of s minus c, that distance from the center point is equidistant, right? It's on a sphere, so it's always this r. But if I square that, I get alpha minus c dot alpha minus c equals r squared. Differentiate that. That gives me alpha prime, which is the tangent, dot this radial vector, right? Alpha minus c equal to 0. Differentiate again. That gives you t prime, dot the radial vector plus t dot t equal to 0. But t dot t is 1 and t prime is kappa n. So that gives us that that gives me that minus 1 over kappa is equal to n dot the radial vector. But there's a Cauchy-Schwarz inequality, right? So the magnitude of a dot product is less than or equal to the product of the magnitudes of the vectors dotted. And so that then gives me, this has length 1, right? N has length 1. The length of alpha minus c for any s is equal to r. So this can at most be r. So this gives us that the reciprocal of the curvature is less than or equal to r. In other words, the curvature is greater than or equal to 1 over r, which means that the smallest curvature possible for a curve which lies on a sphere, right, is 1 over r. And so in particular it would be like this curve. The equator, for example, is one of the great circles. That would actually have curvature equal to 1 over r. But if you take other curves other than great circles, you'll have curvatures which are smaller than that 1 over r. And that brings us to the non-unit speed case, which I'll talk about separately. Thanks. That concludes part 1 of lecture 6.